Hello, welcome everyone. So it's my pleasure to introduce for you the speaker of the day. So it's a joint colloquium, and QuMat. And the speaker of the day is Samir Lounis, who is here. Samir is coming from Algeria, where he did his magister thesis. And then he moved from, he did this in collaboration between Algeria and France, and then he moved to Germany for the PhD, where he did his studies with Stefan Brucker and Lederix in Aachen University, which is not very far from here. And then he liked the place very much, so he basically stayed there. And he went through his career as a junior professor first, and then as a associate professor in Duisburg, and now he's just been promoted to full professor at the University or Martin-Luther University in Halle. So his topic is quantum theory of solids. This is the chain, the name of his chain, so you can ask whatever you want regarding this topic. And the talk of today is focusing on Spinorbitronics. Spinorbitronics in the nanoworld, from all electrical detection of skyrmions to Kagomerization. Now, if there is anything that you want to ask me, just don't be shy and go ahead. And the talk is prepared for 50 minutes plus question, but like if there is some concept that you want to ask, just raise your hand and interrupt. I mean, this is for you to enjoy, so you should be able to, to interact lively with our speaker. And so, Samir, the floor is yours. Enjoy your audience here.
Yeah. Hello, everyone. Thank you very much, Zeila, for the kind introduction. I would like also to thank you for the invitation. It's a pleasure to be here. It's my first time in Utrecht, and so far I'm enjoying it very much. Yes. So, as you mentioned, I will be discussing Spinorbitronics in the nanoworld. And today, I would like to focus on the physics of what is called magnetic skyrmions, which is this kind of magnetic object which looks like what I call magnetic flower, so to say. So this talk lies in the field of magnetism. And we all know that magnetism has been very crucial in our civilizations, in our societies, provides, or in our technologies, it provides powerful ways to store information in the long run, and that explains why most of information stored worldwide is based on magnetic concepts. And that is basically the working principle of such a hard disk drive. On the surface of this disk, you have atoms that act as atomic magnets with, so to say, a north and a south pole. And this is the result of a quantum mechanical property, that is, electrons building up this atom carry a spin angular momentum, which make up then a magnetic moment. And the direction of this magnetic moment can be associated, so to say, to the north pole, for example, of this atomic magnet. And it is thanks to through this direction of this magnetic moment, then one encodes information on such a hard disk drive. That's what defines the binary information and the zeros and ones that you have on a hard disk drive. Well, it turns out that what defines the magnetic bit is not just a single atom on the surface, although there is a large community trying to realize that, encoding information at the level of a single magnetic atom. But on such hard disk drive, what defines a bit is basically a domain made of magnetic moments, many of them, such that all these moments point in one direction or the opposite. And to have these moments aligned in such a direction, you need an interaction, and the interaction, for example, here is mediated via electrons that hop from one atom to the next. And this gives rise to a magnetic interactions that I can write down in the following way, in such a Hamiltonian, a Heisenberg Hamiltonian. And this interaction imposes then a magnetic alignment of the moments in a single direction. Well, this kind of technology is basically based on collinear magnetism, right? That all the moments have to point in one direction or the opposite. And this is facing today huge challenges, this kind of technology, because our societies are producing a huge amount of information that we want to store in smaller and smaller places. And we basically would like to have this information accessible all the time. We would like to be able to play with this information all the time. We would like to analyze it. We would like to play with it. And we would like to store the new data induced by this type of information. And with the rise of AI, this, of course, makes it very challenging from the point of view of energy cost and time in reading and writing information. So this calls for paradigm shifts. And one way to address the challenges here is to basically, a very important field of research that tackles these kind of problems is spintronics, or second generation spintronics. So that is what is called Spinorbitronics. And in this room, we have many experts in spintronics. And the idea here is basically try to harness the interplay of the different degrees of freedom of the electron, charge, spin, and orbital degrees of freedom. And all of these can couple, for example, with spin-orbit interaction. This is a relativistic effect. The interaction is, in principle, rather small, but its impact on the physics of materials can be tremendous. It has a strong impact on energetics. It can give rise to intriguing, exotic, fascinating effects, which can have implications in technology. So if we get back now to this fundamental magnetic bit and then move, yes?
On this previous transparency,
yeah.
How would that energy forecast change if you would some kind of switch to spintronic?
Well, we don't know. Yes, we don't really know. We want to reduce the energy consumed within these processes, but we need to find the right concept that reduces dissipation in the mechanisms that are involved in reading and writing the information. Whether we would achieve this is not so clear. Mm-hmm.
Isn't the main energy cost in currents flowing in different elements?
Yes.
And if you have spin current, then you can calculate.
Yes. But there is also a cost in transmitting the information from one place to another. I think that you would have a huge gain in the energy needed to make the information stable. Yeah. Mm-hmm. So if one wants to go beyond this paradigm shift of having all these magnetic moments pointing in one direction, so beyond this paradigm of collinear magnetism, one possible solution is to enable these magnetic moments to be misaligned. And this defines then non-collinear magnetic bits, and this is one example. This is this magnetic flower I've shown earlier. That is a skyrmion, what is called a skyrmion. And if you look carefully at the spin texture, you'd realize that the magnetic moments rotate smoothly from one direction in the center to the opposite at the edge. And you have to imagine that the spin texture is immersed in an otherwise ferromagnetic background, for example. So this magnetic object is confined in 2D and behaves like a particle. And it turns out that once you create it, it is very difficult to destroy. There is an energy barrier that protects it. And this kind of magnetic textures actually gives a wonderful playground to explore not only physics that comes from Spinorbitronics, but also topological concepts, because this object is topological by nature, as I will explain in a few minutes. So this magnetic texture can have quite intriguing properties, which once more can be of interest for information technology. So if you look very carefully at this spin texture, you see that the magnetic moments follow a unique sense of rotation. And this is dictated, in this case, by a relativistic interaction, and that is what is called the Jaluzinski-Mourier interaction. So it is there whenever you have broken inversion symmetry and spin-orbit coupling. So one kind of family of materials where these can emerge is such interfaces involving heavy metals, so atoms which have then strong spin-orbit coupling, which are interfaced with a magnetic film. And the role of these atoms having a strong spin-orbit coupling is that they mediate the interaction between these two magnetic moments. So there is a scattering of the electrons at this spin-orbit coupling site, move then to the next magnetic atom, and this gives rise to this Jaluzinski-Moria interaction. And such an interaction gives rise to broken chirality. So if I take these two spin spirals, magnetic spirals, you see that in principle they are kind of similar, the sense that the absolute angle between two adjacent magnetic moments is the same. But the sense of rotation is different. In one case it is clockwise, in the other it is counterclockwise. Such an interaction can be written in these terms. It would contribute in the following way to this Heisenberg Hamiltonian that I've introduced earlier. So I have here the typical Heisenberg exchange term, can have here a Zeeman term, and in between you have this, what I would call now a chiral term. It consists of a mixed product involving a Jaluzinski-Moria vector that is dotting a cross product between two magnetic moments. And this defines what I call a two-spin vector chirality. If I switch the sense of rotation of the moment, this term picks up a minus sign. So it would affect the energetics. And this would depend on whether this Jaluzinski-Moria vector points towards you or towards a slide, and it will favor then one or the other magnetic state. So this is about chirality. How about topology? So this spin texture, we know, this skyrmion, is different topologically from such a ferromagnetic state. And this I can demonstrate without writing down an equation. So for example, for this cup, I know that it is topologically similar to this donut because I can deform both from one to the other form without any abrupt transition. Can have a continuous deformation for that. If I apply a magnetic field on these two domains, nothing happens to the ferromagnetic one, but you see that the skyrmion has to get squeezed because you will have more magnetic moments aligned to the field till ultimately reaching the limit where one magnetic moment is pointing in the opposite direction than the rest of the ferromagnetic background. Obviously, to get back to this ferromagnetic state, I need an abrupt transition. So topologically, these two structures are distinct. How do we monitor topology here? This is done via what is called a topological index, a topological charge, which consists of a mixed product of magnetic moments. So this defines the solid angle between three magnetic moments. So in a way, what we are measuring here is the non-coplanarity of the magnetic moments. But if you sum this non-coplanarity over a whole skyrmion, what you would do is to count how many times you would wrap such a two-dimensional spin texture on the surface of such a sphere. For the case of the skyrmion, then the magnetic moments of the center would be located at the south pole of the sphere, while the edge moments would be located on the north pole. And if you get from this an integer number, then we're dealing with a skyrmionic spin texture. For a ferromagnet, I would get a 0. So the interplay of chirality and topology can give rise to intriguing properties. For example, I mentioned earlier that electrons carry a spin angular momentum, which gives rise to a spin magnetic moment. Electrons that orbit around an atom carry also an orbital angular momentum, which gives rise to an orbital magnetic moment. However, such a moment in a solid gets quenched because of the crystal field, because you have symmetries that are imposed by the crystal field that makes orbitals degenerate, and that cancels out the magnetic moment, the orbital moment. So in a solid, usually to get such an orbital moment, you need spin-orbit coupling to couple to the spin, and then this gives rise to an orbital moment. But in here, we found a few years ago that there is a new type of orbital moments that can be triggered by the non-coplanarity of the magnetic moments. So the moment here is delocalized, and you see here electrons that scatter at 3 at least non-coplanar magnetic moments. And analytically, you can show that such an orbital moment is directly proportional to this mixed product of spins, which is called 3-spin scalar chirality. It's a scalar object. Now, as you can imagine, so this moment then is independent from spin-orbit coupling, and if it is summed up over a whole skyrmion, it becomes then topological, right? Because it would be then proportional to the topological charge, as shown in this figure. For different skyrmionic textures, the orbital moment gets quantized. And in this paper, we explain how to measure such an orbital moment and how to distinguish it from conventional ones that are induced by the presence of spin-orbit coupling using, for example, X-ray magnetic circular dichroism. Yes?
Quick question. The formula for the 3-spin scalarity is basically the volume that's spanned by the magnetic moment.
By 3 moments, yes.
Yeah, so cross-product times gives you the volume of whatever.
Yes, it gives the solid angle.
Does that allow some kind of physical interpretation of how the topological index should be thought about?
Yeah. So it defines the whole solid angle, carried by the whole object, because then it is summed up everywhere. Yes. So it is interesting that one can probe basically topology by looking at the orbital moment. That is what is quite interesting, that topology and chirality reaches such basic and fundamental quantities. This also, chirality and topology, impacts transport. And I think we have several experts in transport in the room. And very often this is explored in what is called Hall effects, which means transport in the plane of the skyrmion, where we have contributed with some works, but I will not discuss this today. So, summary, skyrmions, since they have been proposed theoretically, they have been basically observed everywhere in all kinds of materials across dimensions, going from bulk, films, multi-layers, and they can carry various names because they are characterized by distinct properties. Early on, they have been proposed to be utilized in devices, and let's say what became by now the conventional example is this rest track memory device, where, if you see it clearly here, I'm not sure, where you would see that here pulses are impinging this rest track memory device, which is then used to induce magnetic skyrmions on this rest track, and then they would move across the track. So in a sense, here the skyrmions act as dynamical magnetic bits, which contrast with the static bits that you have in a hard disk drive. Okay, so to bring this potentially into technology, and someday information technology, the community agreed on some kind of conditions that these objects have to satisfy. And today, I would like to focus on 3 aspects. I would like to address efficient ways of detecting such spin textures, address a fundamental problem of these skyrmions, that is what is called the skyrmion Hall effect, which I will introduce later on, and then introduce a new platform to realize rather small skyrmions, which are sub 10 nanometers, which are very then useful to increase storage capacity. So how do we look into these problems? I'm a theoretician, so what we do and what we have been doing for many years is to develop concepts, theoretical concepts that are based on density functional theory or other techniques. And our effort has been in developing what we call the Koringa-Kohn-Rostocker green function method. And with such a method, today we can fully simulate lattices of these 2-dimensional or 3-dimensional spin textures. We can also simulate single magnetic skyrmions embedded in an otherwise perfect material, because we use green functions, and this enables the possibility of using embedding techniques. So we can have direct access to the electronic structure of these large magnetic objects. We can also map magnetic interactions from such techniques, which would be used then to parameterize an extended Heisenberg Hamiltonian, and whose dynamics can be explored by solving the Landau-Lifshitz-Gilbert equation. So today we'll address results obtained with some of these techniques. So let me start then with my first topic. And this is the work of Imara Fernandez. And what we did in this work is to try to think of ways of detecting such spin textures in current perpendicular to plane geometry that is different from this Hall effect geometry, which is current into the plane. Which means here that I have an electrode that is sitting on top of my magnetic material, and I want to look at transport between the two electrodes in this perpendicular geometry, which is the conventional one used in spintronics. That is the working principle of the read head utilized, for example, in a hard disk drive. And there is a little work done on such kind of physics looking at these kind of spin textures. And I would like first to introduce my Drosophila type of system where I would demonstrate basically our findings. And this is basically this iron monolayer, which is grown on iridium surface, covered with palladium. This is well understood experimentally and theoretically. I'm showing here spin polarized STM measurements done in the group of Wittenberg in Hamburg. And what you see here are rows, which actually correspond to the to images of spin spirals. So this is characterized by spin spirals, which are chiral. And chirality here is imposed by the fact of having iridium underneath, which is a heavy element that gives rise to a Jaluzinski-Moria interaction. Upon application of a magnetic field, these spirals get deformed and then form disks. These are the disks shown here, which have a size of a couple of nanometers. So we can look at such disks fully from first principles. That is a theoretical skyrmion. It lives in iron, but it spin polarizes palladium and iridium as well. And now we're going to look at the underlying electronic structure, which is shown here. So this is the density of states. And what you see for these unoccupied states, which are of minority spin character, is that initially you have two resonances that are far away from each other. So this kind of picture is obtained across the magnetic skyrmion coming from the edge to the center. And you see that in the ferromagnetic region, you get well-defined resonances, and they tend to get closer to each other once we get close to the center of the skyrmion. Looks like a strange effect, but one can explain it with simpler arguments. As you know it from quantum mechanics, if you have two orbitals that hybridize, then you get a bonding and an anti-bonding state. Bonding favors bonding between different electrons, anti-bonding disfavors it, and therefore bonding is at lower energy. And it turns out that this gap can be modified if these orbitals carry a spin angular momentum, if they are magnetic, and if you play with the misalignment of the magnetic moments, the gap can change and can decrease. So as soon as we found this, came the idea that in principle, you can use this to probe a skyrmion moving in a rest-like memory device, but then you would use an electrode that is non-magnetic to detect it. So we're talking about all electrical reading. So the current that flows from the both electrodes would scatter differently at the electronic structure induced by the magnetic skyrmion, which is different than of the ferromagnetic one region. And that's what we call spin mixing magnetoresistance, or would lead to what we call a spin mixing magnetoresistance, because this effect is induced by the way electronic states hybridize, change, upon misaligning the magnetic moment. So the spin mixing magnetoresistance here, what I call here XAMR effect, reaches a magnitude of 20%, which is rather large. And it is of the same order of magnitude than what has been measured and published within the same year by the group of Wittenberg. So this is, of course, very useful to use a non-magnetic electrode to probe something that is magnetic. So it's nice to see this contrast, and this has been then utilized a lot in this field to explore such magnetic textures. It is very, very useful in technology, right? You don't need to bring in a magnetic electrode to look at these properties. And in the field of scanning thalamic microscopy, it's very difficult to manufacture such spin-polarized STM tips. So it makes it very useful. Well, what would be even more useful here is to know how to correlate the contrast you see here to the direction of the magnetic moment. Then you would learn about what you're looking at. Just observing contrast doesn't help very much. And here it is then very educational to compare this magnetoresistance to the more conventional ones. Conventional one would be, for example, the giant magnetoresistance, so what is called standing magnetoresistance, for which Aberfett and Peter Grunberg got the Nobel Prize in Physics. And what you see, I mean, here you've got two magnetic electrodes that are involved, and here we know that the conductance is directly proportional to the dot product of the magnetic moments. So if you perform a TMR measurement, then you can use this to learn something about the direction of the moments of what you are exploring. You can also detect magnetism with a non-magnetic electrode via what is called the AMR effect, anisotropic magnetoresistance. Here the effect is induced by spin-orbit coupling in second order, and one can write it down in the following way. The conductance would be proportional to the projection of the magnetic moment on some local anisotropy axis. It is squared, which means that within the TMR effect, you cannot distinguish a moment pointing upwards from a moment pointing downwards, but any misalignment could be seen. XAMR also involves a non-magnetic electrode, but the dependence turned out to be very complicated. But there is a very nice study by Kobetska and co-workers who analyzed all the data available, and then they realized that for a large bias voltage, these kind of magnetoresistance are proportional to the average angle between a magnetic moment and its nearest neighbors, just the angle. And this was very surprising, but it worked. And since then, it has been used a lot to understand contrasts that have been observed in other materials and other systems. So this triggered our curiosity, and then we decided to look into the problem. How do we do that? We use a multiple scattering approach. And the idea is the following. We would like to monitor how the charge at the level of this atom changes upon misaligning the magnetic moments from the neighborhood. And electrons, we follow the scattering of the electrons at the neighboring atoms, and these electrons pick up this information. So you can have a scattering process where an electron comes from this atom, hits this atom, and then gets back, or it can follow this scattering process to the second atom, and so on and so forth. And by doing this carefully and analytically, we find that a fundamental contribution to this magnetoresistance would be isotropic in nature, and it involves a double scattering between two magnetic potentials. And this is directly proportional to the dot product between magnetic moments. So it looks like the Heisenberg exchange interaction, but I'm not talking about an interaction, I'm talking about a charge. I can also find a term which is chiral. Here the scattering goes through a spin-orbit coupling site. And this gives rise to something that looks like this Jaluzinski-Mourier interaction. And changing the chirality of these spin states, or the sense of rotation of the moment, then changes the contribution to the charge. And this chiral vector is very similar to the DMI vector within a simple model like a Rashba model. We can recover the AMR effect, which involves a double scattering at the spin-orbit coupling site, but only one magnetic potential, and we discovered a non-local contribution which involves a second magnetic potential, and that's what I call XAMR. So this approach is very powerful, and in the years we have used it a lot to understand and find new type of interactions of high order origin going beyond, for example, the DMI, and new contributions to the Gilbert damping and so on and so forth. So here I'm categorizing these magnetoresistance in terms of the presence of non-collinearity and spin-orbit coupling in first and second order. So AMR would be purely second-order spin-orbit coupling. IXAMR would be fully non-collinear, or just non-collinear. The chiral magnetoresistance is first-order spin-orbit coupling, similar to the DMI. And then because of this cross product, we expect a dependence which is linear with the angle. And this explains what has been measured for many years with these magnetoresistance. What they have been looking at is a chiral signal. XAMR will be a mixture of both non-collinearity and second-order spin-orbit coupling. So overall, the magnetoresistance consists of various contributions which are induced by different mechanisms, distinct mechanisms, And therefore, the angular dependencies are also different, which means that they can be measured and extracted experimentally. And if you are able to do that, then you can really have a very good picture on this on the complexity of the spin textures measured with a non-magnetic electrode. One can do that, for example, by changing the size of these magnetic objects upon application of a magnetic field. The efficiency of these effects is very large, what this table is showing. So they can be counteracting each other. They can be additive. They can be dominant ones. AMR usually is rather negligible. And here is a two-dimensional map of these contrast, where you see clearly, we'd like you to focus on what happens to the conventional AMR signal to this new AMR effect. Besides the difference in the efficiencies, one sees that in the conventional AMR, there is no distinction between the core of the magnetic skyrmion from the surrounding, which is different in the non-local AMR effect. And this theoretical spectrum, as function of bias voltage, shows that there are indeed large regions, bias voltage regions, where the chiral signal dominates over this AMR or this AMR signal. So overall, this basically shows that these magnetoresistances are very useful to explore these complex spin textures, explore their chiral nature in this perpendicular geometry. All right, now we'd like to switch gears and discuss a problem that is met by these spin textures, which is what is called the skyrmion Hall effect. So whenever you try to drive them with a current, these skyrmions get deflected because of a Magnus force, which is known to be proportional to the topological charge. And this is something that you don't want to have in a device, right? If you want to drive your skyrmions around, you would like them to move in a straight line. You'd like to have a full control of their motion. But in practice, this doesn't happen. And if you want to realize this in a racetrack device, then usually these skyrmions hit the edges, and then they get annihilated. And a way of solving this problem has been proposed a few years ago, and that is by considering a hybrid type of skyrmions, antiferromagnetic skyrmions. So if you have two skyrmions of different magnetic nature, they carry an opposite topological charge, so they should be deflected in opposite directions. But if you make them couple, then they would move in a straight line. So that's a way of canceling this effect. And such an antiferromagnetic skyrmions then are expected, besides the absence of the skyrmion Hall effect, to have no stray field, which makes them then easily small, and they should be robust to external magnetic perturbations. Problems is that they are difficult to detect, but the XAMR effect I mentioned earlier should be fully sensitive to such spin textures. And the other problem is to manipulate them. So in principle, antiferromagnets are more abundant in nature than ferromagnets. And many of us try to figure out where to find such skyrmions, and this is turned out to be a very hard task. So few teams have been successful. From the experimental side, they have been realized in what is called a synthetic form. So here you have ferromagnetic films, each hosting a ferromagnetic skyrmion, separated by a spacer. So if you choose the spacer properly, then you can design it such that the coupling between these skyrmions is of antiferromagnetic nature. And these have been observed. Skyrmions in the intrinsic form, meaning that they are realized in the same material, have not been seen yet. In bulk, they have been observed that they show up in a really complex form. So one can say that down to a few monolayers films, intrinsic skyrmions, antiferromagnetic skyrmions, have not been seen yet. And this is kind of surprising, because if you compare to the realm of ferromagnetic topology, it took just a couple of years to move from bulk to thin films. And this is something that we wanted to change by predicting a realistic combination of materials to observe such magnetic textures. And that is the work of PhD work of Amal Darawshi, who finished her thesis basically end of last year. And as I said, many of us try to find these kind of skyrmions. At the model level, many people propose to look at square lattices to generate them. but this turned out to be unsuccessful. So our strategy was then to start with a material that is known to host ferromagnetic topology. And these are, for example, this iridium surface I introduced earlier. The idea is very simple, just to interface films which can be antiferromagnetic on such an iridium surface. And today I'm going to talk about the case of chromium. And we consider here, we have to do things very carefully. We have to consider all kinds of interfaces, all kinds of scenarios. And I'll choose one of them today to discuss this particular case. What is important to keep in mind here is that on such an FCC surface, along the 111 direction, you expect a hexagonal lattice. And if you put an antiferromagnet on a hexagonal lattice, you expect magnetic frustration. So if I have 3 atoms, then I know that the ground state cannot be this, and it cannot be collinear, but must be a Néel state with a 120 degrees angle between moments. The surprise, however, is that for this chromium layer, we get a collinear state with a row-wise antiferromagnetic state. So you have rows of moments pointing in one direction or the opposite, alternating, all perpendicular to the surface, as dictated by the magnetic anisotropy energy. What happens here is that the magnetic interactions are not limited to the nearest neighbors, as for this trimer. You have interactions beyond the nearest neighbors. You have RKKY interactions, and this matters. That is what is shown here. The magnetic interactions for the nearest neighbors is strongly antiferromagnetic, then decreases to a little bit for the second nearest neighbors, and then there is a switch of the magnetic nature for the third nearest neighbors. Actually, these are the 3 ingredients needed to get such a row-wise antiferromagnetic state. You see, for such a configuration, the nearest neighboring interactions, the nearest neighbors here, the majority of them, 4 out of 6, are happily coupled, aligned in an antiferromagnetic fashion to the central one. Same is true for the second ones, and the third ones are all aligned ferromagnetically. So this is one point in the phase diagram describing these kind of materials in a hexagonal lattice, and this is quite satisfied for this peculiar case. So overall, the ground state is a row-wise antiferromagnetic state, and here emerge intrinsic antiferromagnetic skyrmions of different sizes. I mean, here below 10 nanometers. What was surprising is that we get them catenated. They form dimers, they can form chains, they can overlap, which is very surprising because usually ferromagnetic skyrmions repel each other. They don't like to overlap. And this happens obviously because of the antiferromagnetic nature of this material. In this particular case, there is iron underneath chromium separated by palladium, and there is topological life in iron. You get spin spirals where ferromagnetic skyrmions can emerge. So what we found here is a unique scenario where topological ferromagnetism meets antiferromagnetic topology. So you can be in a scenario where an antiferromagnetic skyrmion can interact with a ferromagnetic skyrmion, living in iron, the other one in chromium. So you can have pinning effects, you can have deflections, and this gives several opportunities to design basically your material to transport one or the other magnetic object. So let me explain a little bit how these skyrmions form in this hexagonal lattice. So we have one layer, and it turns out that it is very useful to decompose it into sublattices, which are hexagonal. There are 4 of them. And in these sublattices, these atoms are third nearest neighbors, which means that the coupling, if you remember what I said earlier, is of ferromagnetic nature. Added to that, you have a Jałodziński-Morier interaction, you have a magnetic anisotropy energy, so you can have a ferromagnetic skyrmion here, but it cannot live on its own. It would just annihilate if you create it. So it needs its twin brother, so to say, in the adjacent sublattice, antiferromagnetically coupled to it. So this gives rise to the minimal ingredients to generate these highly sought intrinsic antiferromagnetic skyrmions. So what explains now this overlapping between the skyrmions is the following. You have mechanisms that are in competition, mechanisms that favor repulsion when the skyrmions are generated in the same magnetic background, like ferromagnetic skyrmions would do. They would repel each other. But this is overweighted and dominated by mechanisms involving backgrounds which are of opposite magnetic nature. So the goal in doing all of this is to explore or to come up with materials that would have a vanishing Hall effect. And we looked at it. We checked it. We checked it in this peculiar geometry, which is a magnetic tunnel junction. So we have a magnetic electrode, right, on top of this electrode hosting these chromium antiferromagnetic skyrmions. This is impinging a current, which is spin polarized, and this will introduce a spin transfer torque on these magnetic skyrmions. And one expects that the motion of the skyrmion would go perpendicular to the polarization of the current in such a geometry. And indeed, there is no skyrmion Hall effect. Skyrmions move in a straight line. But if you misalign a little bit, or if you rotate a little bit this current polarization, one gets a deflection. So there is also skyrmion Hall effect. And the reason for it is that the skyrmions generated here are of elliptical shape. So they are anisotropic. And this ellipticity turns out to be a universal behavior on this triangular lattice. Ferromagnetic skyrmions would be isotropic in there, but antiferromagnetic ones not.
What breaks those?
Yes.
What breaks what causes the symmetry of that?
Yes, so the symmetry breaks down, and that is what is shown here. So if I take just a regular hexagonal lattice, interactions are the same in all directions, right? But as soon as I add another sublattice of antiferromagnetic nature, then I expect that the coupling along this direction would be completely different than this one, which gives rise then to this ellipticity. So as I say, this is a universal behavior, and the degree of anisotropy is related to the underlying magnetic interactions, of course. So we have ellipticity, we get this Hall effect, and this is what is shown here, quantified. That's the Hall angle. So that's the deflection of the, that is related to the deflection of the skyrmion with respect to the direction of the applied current. So you see that it follows an oscillatory behavior with a Hall angle of almost 6 degrees. But one identifies here magic angles where the skyrmion Hall effect vanishes. Velocity also follows an oscillatory behavior. And you see angles where it reaches maxima or minima, and the difference in the velocity here is about 100 meters per second. So I think this gives nice opportunities in this field of antiferromagnetic skyrmions, because in this particular case, we have the ability in principle to control the motion and the speed of these skyrmions by controlling the polarization direction of the impinging current. So imagine you apply current, your skyrmion moving in a straight line in a two-dimensional, of course, film. And then you want to switch the direction of the skyrmion. You just rotate a little bit the polarization of the impinging current. Then it moves to the next level. And then you bring in the initial direction. And then your skyrmion would move in a straight line. So you'd have multiple tracks, in principle, in a two-dimensional platform. But not only that, you can also control the velocity. You can decelerate or accelerate your skyrmions depending on the direction of the polarization of the current. So now I would like to move to my last topic, and this is, yeah.
Quick question. So
Yeah.
you only showed skyrmions living on 2 layers. Is there something preventing them being on all of these layers now, or is it just energetically not?
So these skyrmions live in a single monolayer. And what
In your construction.
and yes, and then in the construction I split them up such that I can find the optimal sublattice to get my ferromagnetic skyrmion, and the ingredient for that is that magnetic interaction, which is of ferromagnetic nature. But if I have just a single antiferromagnetic skyrmion, they would live just in 2 sublattices. Yeah. And I know that this is under scrutiny from the experimental side, try to find them in these materials because they are accessible. Yeah, I would like to address my final topic here, and this is the work also of Han Zhu. She finished her PhD very recently. She defended her thesis before the end of the year. And here I wanted to discuss something because also Zeila is very much interested in boron nitride. We discussed boron nitride earlier. And I'm working a lot also on two-dimensional van der Waals heterostructures, which are very interesting for different reasons. And what we wanted to do here is to consider a hybrid interface where you have then this boron nitride interface with the materials I mentioned earlier, which are the fundamental materials used in spintronics. Why did we choose boron nitride? Because there were predictions showing that, for example, these chiral interactions can be modified by boron nitride. But what Han discovered is the following. If you put such a boron nitride layer on a hexagonal lattice, you have a dramatic structural reconstruction. You start with a hexagonal lattice, and you end up with a Kagome structure. And I find this very fascinating. This movie, in principle, should show how the atoms move around. The blue atoms, in this case, are cobalt atoms. The gray atoms are platinum, is the platinum surface atoms. And these light blue atoms are nitrogen atoms. So what happens is that the cobalt atoms move underneath the nitrogen atoms. In the hexagonal lattice, 1 out of 3 cobalt atoms would be underneath a nitrogen atom. But in the Kagome structure, the 3 out of 3 would be underneath. So every nitrogen atom would have underneath a cobalt atom. So it has to do somehow with nitrogen, which is highly electronegative and is capable to move these atoms on such surfaces. A surprising effect, and then we looked at it very carefully. Hangyu did very intensive and careful simulations, and turned out to be a general behavior. So she considered all kind of a series of 3D magnetic films on various surfaces, say platinum, gold, and silver, and she always finds this Kagomerization to happen. There are only 3 cases where it is not stable. That is the case of manganese, scandium, and titanium. But I believe there is an energy barrier that protects it if one can realize it. But it seems to be a very robust kind of behavior. And I find this very, very nice and very exciting because it shows in principle that you can use spintronics materials to explore Kagome physics down to the single magnetic monolayer, because we're dealing here with single magnetic monolayers, which can easily be realized experimentally. And of course, Kagome physics is very interesting. You can have complex magnetic behaviors that can emerge, spin liquid behavior, quantum spin liquid behavior, exotic electronic structures, properties that can occur, Dirac cones, flat bands, correlations, transport properties. In general, this kind of physics is explore the kind of complicated materials, right, which are not purely two-dimensional. And so I find it very nice that one can look at such physics in principle, as I said, with these transition metallic films. So here I'm showing the energy difference between the hexagonal lattice and the Kagome lattice as function of the atomic number of these films. And from this picture, you see that most of the films prefer to be in a Kagome structure. And it is easier to form these Kagome structures on silver and gold than on platinum. But what is striking here is something that you may have noticed, right? That the shape of these energy differences is rather similar. Looks like an M shape with a minimum at half filling and maxima on the side. And this tells us that it has to do with the D-band filling of the electronic states of these films. And this is known in bond theories, bond concepts used in catalysis, used in formation energies, cohesive energies. This is a universal behavior that is known. This is an example of cohesive energies for transition metals, bulk materials, 3D, 4D, 5D elements, and you see this inverse parabolic behavior with a minimum at half filling. And this was explained already many years ago, within the same years in the 60s, by Jacques Friedel. So this has to do with the way you populate electronic states across the series of transition metals. Initially, you occupy bonding states. The bonding states I introduced when I discussed the skyrmion, if you remember. And this favors bonding, obviously. And as soon as you reach half filling, at some point you start to populate anti-bonding states, these higher states, which of course disfavor cohesion. Now, if you have magnetism, these bands get splitted, which leads then effectively to a minimum at half filling. So, in principle, if I have this figure, then I can predict in advance what would be the materials best to realize this Kagomerization. And the ingredients, the mechanisms that are at play here is nitrogen atoms that are capable to pull out these transition metallic atoms on the surface because of the strong electronegativity. And what is, so of course these atoms are bounded to these heavy metallic surfaces. But the interesting aspect there is that these heavy metals have a large lattice parameter, and usually these 3D transition metals have a smaller lattice parameter. So the cobalt atoms would like to move around, and this is then favored by the presence of nitrogen on top. What makes it easier for silver and gold to form these Kagome structures is that, in contrast to platinum, which has strong electronic states around the Fermi energy, this favors strong hybridization with these atoms on the surface, and then this makes it more difficult to move the atoms around. I don't know whether I have some time, Zeila, or yes, okay. So, yeah, I think here I just summarized that the important thing is that all electronic properties known for these Kagome structures happen also on these interfaces. That is what is basically aimed to be shown in this slide. So you see flat bands that occur in these different type of interfaces. And it turns out that probably using silver as a substrate is the more appealing one to observe clearly such flat bands and Dirac cones. And the reason for it is that there is a kind of a pseudo gap in silver and gold in contrast to platinum. That would be here my summary. From the magnetic point of view, there is of course rich physics, because switching having such strong structural transitions can change the topology or the nature of the topology of the magnetic textures that are realized. For example, you can go from such a skyrmionic structure to realize some bimeronic structures. So this brings me to my conclusions. What I introduced today, and I've tried to explain, hopefully in an educational way, is that there are interesting magnetoresistances which enable the all-electrical detection of these spin textures in a perpendicular geometry, which is the conventional or the traditional one in spintronics, should be sensitive to chirality, for example. Then I introduced a family of materials or a strategy to realize these intrinsic, highly sought intrinsic antiferromagnetic skyrmions, which have not been seen so far, down to thin films, and I propose to look at triangular lattices. And in this family of materials, what we've discovered is that there is a rich set of transport and dynamical behavior which can be useful. And finally, I introduced what we predicted here, the possibility of Kagomerizing 3D films utilizing boron nitride, which can be, usually it is utilized or considered just as a protective material, but it shows here that it can be functionalized to create these kind of intriguing structures. Finally, I would like to acknowledge the main people who did the work. And here I would like to highlight Hangyu Shu and Amal Darouchi and Imara Fernandez and funding. Thank you for your attention.
Thank you, Samir. So now the talk is open for questions. So we have a few minutes to materials.
Thank you very much.
Thank you.
I had a follow-up on Tomislav's initial question
Okay.
about the presence of currents as opposed to spin currents. In your AFM skyrmion manipulation, you're changing the polarization of the current, but it's still a charged current that you're playing with, right?
So here you have a spin current that is flowing in.
Pure spin current, so no.
Yes. So yeah, there is a spin angular momentum. Yeah.
If I can avoid charge currents, then
Here,
a lot less.
yes. So here the idea is not to come up with, let's say, manipulating these magnetic textures. The goal is to manipulate these antiferromagnetic skyrmions. And for that, you need a torque. And the question is which kind of torque you can utilize. And then you have to choose the geometry very wisely, because some of these torques are not efficient if they are not applied in a proper way. So the goal there was not to come up with the most efficient way to manipulate these skyrmions, but to be able to explore the skyrmion Hall effect for these objects. That was the goal there. So there will be dissipation in that case. Yeah.
Yeah, no, we're asking a bit much.
Yeah.
AFM completely protected from field and with response to.
Yeah, because the net magnetization cancels out, and you have to figure out how a torque would act on both magnetic moments and move the whole object, right? Which is not that obvious. Mm-hmm.
There was a question here.
A couple of slides ago, there was some size difference between the skyrmions.
Yes.
What caused it? Because it feels like the bigger one could be this one.
Yeah, so these magnetic skyrmions, I mean, if you take a ferromagnetic skyrmion, for example, I've shown at the beginning when I introduced this concept of topology, an effective magnetic field affects the external magnetic field affects the size of this ferromagnetic skyrmion, so it can get affected. The same thing is happening here, but the reason for it is that you have skyrmions occurring in other sublattices, and this effectively leads to an effective field that acts on the skyrmions themselves, and therefore there is this kind of change in the size. Mm-hmm.
Yeah, one there. Yeah, please.
I've heard that these topological protected states can be used to create to develop qubits. Is that possible? Do you think that?
So there are some ideas in. So what I discussed so far are materials where the magnetic moments here behave in a classical fashion, right? So the magnetic moments rotate in a smooth fashion. We are in a limit where the magnetic moments are large, and we are in a metallic regime. So we're talking about, a classical behavior of these magnetic moments. But there are also works, theoretical works, aiming to realize such spin textures, but using quantum spins. And there are ideas that are proposed on how to utilize them as qubits. Mm-hmm.
Oh, okay. Yeah, quickly, and after that we continue.
It's also about information technology.
Okay.
But it's more about sizes of skyrmions versus sizes of fermionic domains. So what's the information density that these skyrmions can have in a nice scenario?
So you see these skyrmions that I've shown in this. Of course, you have skyrmions of when I introduced this at the beginning, where these skyrmions are observed. You have skyrmions of different sizes. They can go up to 100 nanometers. Maybe some of them are much larger than that. Few of them, for me, the best is those which are realized in these thin films, where the skyrmions then are a couple of nanometers. I think this is a huge density if you are capable of doing something with that. But then there is a problem, because you want to detect these objects. You want to be able to detect these objects. And that is where the challenge is, how you do that. If you do that with STM, we know that in practice, this would be very difficult. So there is a trade-off on the ability of detecting the smallest skyrmions with usual means. Let's say in a tunnel junction. STM can do this very well, but at the level of some industrial applications, I think we are still far away.
Okay, so with this I suggest that if you want to continue the discussion, we can do it outside, so people that need to leave, they can do it. And we thank our speaker again.
Thank you.